Welcome back to the deep dive. Ever stop to think about why your brand new phone or laptop sometimes just hesitates? We talk a lot about battery life, sure, but maybe the real slowdown is like the speed limit inside the chips themselves.
That's exactly it. Silicon CMOS technology, it's the absolute workhorse. Think of it like the Millennium Falcon, super reliable, gets the job done, everyone has one. But, eventually you hit a wall, you hit light speed, and that's it.
Right. We're basically pushing silicon as far as it can go before physics itself starts getting weird.
Yeah, quantum effects start messing things up. So if
Yeah.
silicon is stuck at light speed,
We need a warp drive, something faster, something fundamentally different, maybe even atomic.
and that warp drive potentially comes from these things called two-dimensional materials, 2D materials.
Okay.
These are materials literally just one atom thick, and they have these absolutely mind-blowing electronic properties, especially for things like computer memory, that promise speeds and efficiencies silicon just can't dream of.
But that's always been the catch, right? How do you take this amazing, super fragile, microscopic thing from a science lab and actually build a working, tough enough for the real world computer chip in a factory? That jump from the lab bench to the fabrication plant, the fab, that's been the huge gap.
Exactly. It's been the missing link.
And that is precisely our mission today. We're diving into a really systematic, integrated approach that seems to have finally done it. They've built a fully functioning computer chip using these futuristic 2D materials.
Yeah, it looks like they've bridged that chasm, lab to fab, as you said.
So what's our source for this deep dive?
We're looking at a pretty groundbreaking paper. It was published in the journal Nature, and the title is A Full-Featured 2D Flash Chip Enabled by System Integration.
Okay, Nature, that's a big deal.
It is. The work comes from a team including Chunsin Liu, Yongbo Zhang, Boken Shen, Xinchao Yuan, Zenyuan Cao, and their colleagues. They're mostly based at Fudan University in Shanghai, China, and they've laid out this whole industrial blueprint.
A blueprint, they call. ATOM2CHIM, atomic device to chip. Love the name.
It fits.
So our goal here is to unpack this ATOM2CHP system. How do they take a material, one atom thick in this case, molybdenum disulfide, right?
That's the one, MoS₂.
And turn it into a working 2D NOR flash memory chip that actually looks ready for, mass production.
That's the billion-dollar question they tackled.
Okay, let's get into it.
Yeah.
We've heard about MoS₂ and graphene and these other 2D wonders for years. Why is it so incredibly difficult to integrate them? You'd think you could just, spray paint it onto a silicon chip.
Huh? If only. No, it's really a fundamental clash of worlds. Silicon CMOS technology, the stuff in basically all our electronics, it's robust, it's mature technology, built to take heat, mechanical stress, you name it.
Right, it's been refined for decades.
Exactly. But these 2D materials like MoS₂, they're amazing electronically, but they are unbelievably fragile. We're talking atomically thin. It's like trying to merge a sturdy brick wall with, a single sheet of the finest silk.
Okay, so silk on bricks. But isn't the silicon surface, the wafer, super smooth, like mirror-polished smooth?
To us, yes. But zoom way, way down to the atomic level. Even the best polished silicon wafer still has some roughness. The paper mentions about 1.35 nanometers RMS roughness.
Which sounds tiny.
It is tiny, but for material that's just one atom thick, like MoS₂, that 1.35 nanometer roughness isn't a gentle wave, it's a mountain range.
Oh, okay.
So if you try to just lay that flat 2D sheet over these microscopic peaks and valleys, what happens? You get random stress points, you get tiny air gaps underneath.
And that just kills the electrical performance right there.
Instantly. Completely unpredictable, usually useless. The delicate atomic structure needs perfect, uniform contact.
So it's like trying to put a huge, perfect sticker on a bumpy surface. You get bubbles and wrinkles everywhere.
That's a good way to put it. And then, even if you solve that, the normal way you build and package chips involves a lot of rough handling.
Heat, pressure.
Oh, yeah. Intense heat, mechanical pressure. The researchers call it electrothermomechanical shock, or ETM shock.
Sounds bad.
It is bad. For 2D materials, it's fatal. Those forces would just shred these delicate atomic layers. So you couldn't use standard manufacturing techniques. You needed a whole new game plan.
And that game plan is ATOM2CHP.
That's the blueprint they developed at Fudan.
So you said it attacks two main problems.
Yep.
The physical manufacturing, getting the silk onto the bricks smoothly, and then the electrical side, making them talk to each other. Let's start with the physical part. How did they get that MoS₂ layer down without turning it into confetti?
Okay, this is pillar one of ATOM and 2CJP, the full stack on-chip process. It's all about gentle handling and protection for the 2D material. First up, they needed a better way to apply it.
Not just pressing it down hard.
Definitely not. They developed what they call a conformal adhesion process. Think of it less like slapping a sticker down and more like carefully transferring one of those delicate temporary tattoos. They used a multi-step method involving dissolving a support layer very slowly. This allows the MoS₂ layer to gradually settle down and conform perfectly to the silicon surface beneath it, atom by atom, without creating those stresses or air gaps. It relieves the inherent stress.
Okay, that makes sense. Gentle transfer, perfect contact. But wait, you said the 2D memory parts and the silicon control parts operate really differently. Doesn't sticking them together still cause problems once you turn the chip on?
Absolutely, it would if you just mash them together. And that leads to their second brilliant idea within this pillar, a modular 3D architecture.
Modular, like building blocks.
Exactly like building blocks. They realized trying to make the super fast, sensitive 2D memory cells behave exactly like the tough, conventional silicon circuits was, well, probably impossible.
But they didn't even try.
They separated the functions physically. They built the high-performance 2D flash memory core using the MoS₂ and a special memory stack in one distinct block or module. And then they built the standard silicon CMOS control circuits in another separate module.
Ah, so it's like having two specialist teams working side by side, but they only communicate through a very specific translator.
That's a perfect analogy.
Yeah.
They essentially converted a massive materials headache into a much more manageable interface design problem. How do these two distinct blocks talk to each other efficiently?
Clever. And the final piece of the physical puzzle, avoiding that ETM shock during assembly.
Right. Step 3 was 2D-friendly packaging. They just had to ditch the old high-heat, high-pressure methods. They used techniques like room temperature ultrasonic bonding, which uses vibrations and very low pressure, and also carefully shielded certain areas from electrostatic discharge. Basically, kid gloves for the final assembly.
Okay, so that's pillar one. Conformal adhesion, modular design, and gentle packaging. They solved the physical problem. Now, pillar two, the cross-platform system design. The electrical side, what was the big issue there?
Voltage. Plain and simple.
Voltage.
Yeah, these advanced 2D memory devices, to get that incredible speed, they often need specific voltages, sometimes quite high, sometimes even negative voltages relative to the silicon substrate.
And standard silicon circuits don't like that.
Not at all. Your typical CMOS transistor isn't built for those extremes. If you try to pump, say, a high positive voltage or a negative voltage right next to standard silicon, you risk damaging the transistors, causing leakage current, basically frying the controls. It's like trying to run Formula One race fuel in your regular car engine.
Okay, so disaster waiting to happen.
Yeah.
How did they shield the silicon? Build little electrical bunkers.
That's actually not far off. They designed the specific silicon CMOS circuits that needed to talk directly to the 2D memory to be high voltage tolerant.
Wow.
They used specialized structures, things like isolation rings and deep buried layers within the silicon, to physically and electrically wall off those interface transistors from the rest of the chip. Think of them as, like armored compartments, maybe like shielding the warp core on the Enterprise.
Okay, shields up for the silicon.
Exactly. This allowed the silicon control circuits to handle the weird voltage demands from the 2D memory cells without causing problems elsewhere on the chip.
And part of this electrical design was also choosing the right type of flash memory, right? They went with NOR flash, not the NAND flash that's in most USB drives and SSDs.
That was a very strategic choice. NAND flash is great for density, for storing lots of data cheaply, but NOR flash is generally faster, especially for programming individual bits or small chunks of data.
Which is what you want if speed is the goal.
Precisely. They knew the 2D material itself was capable of incredible speed, so they didn't want the memory architecture to be the bottleneck. They chose NOR for its speed potential. Then, they used careful circuit design techniques, like impedance matching.
Which means?
Basically ensuring all the connected circuits, the drivers, the sense amplifiers handle electrical signals smoothly without reflections or signal loss. It's like making sure the plumbing pipes are all the right size so the water flows perfectly. This ensured they could actually read the data reliably at those high speeds.
Okay, wow. So ATO M2C-CHP. Solve the physical contact with conformal adhesion, separate the tasks with modular design, protect it with gentle packaging, shield the silicon electrically, and choose the right architecture like NOR. It sounds incredibly thorough.
It is. It's a truly systematic, integrated approach.
All right, the moment of truth. They built the bridge, they designed the system. How well did this thing actually work? Give us the wow facts.
Okay, let's talk yield first. Because, making one amazing device in a lab is cool, but can you make lots of them reliably? That's the key for manufacturing.
Right.
The Fudan team tested their full 2D and/or flash chip, and they achieved an overall manufacturing yield of 94.34%.
Wait, 94% on a first-generation, totally new hybrid technology.
94.34%. Yeah, it's honestly staggering.
That sounds better than some established processes.
Well, the benchmark they mention, the International Technology Roadmap for Semiconductors, or IRTS, typically looks for yields around maybe 89.5% for mature flash manufacturing.
And they beat that comfortably.
They blew past it. On their first real attempt with this integrated system, it's a massive validation that the Atom M2CHE blueprint isn't just clever theory, it's stable and manufacturable.
Okay, wow. Factor one, it's buildable. Now, the reason we went through all this trouble, the performance, did the 2D materials deliver on that speed and efficiency promise?
Oh, absolutely. This is where you see the magic of the 2D physics kick in. They use a mechanism called Fowler-Nordheim tunneling.
Okay, fancy name. What does it mean?
It means electrons can essentially take a quantum shortcut. Instead of needing a certain amount of energy to flow over a barrier, like in normal electronics, they can tunnel through an extremely thin barrier almost instantly if the electric field is high enough.
So less waiting, more. Quantum jumping.
Kind of. It allows for incredibly fast switching, and the result. The 2D flash cells in this chip demonstrated 20 nanosecond programming operations.
20 nanoseconds. That's insanely fast for non-volatile memory, right? Memory that keeps its data when the power is off.
It's blisteringly fast. And here's the other kicker, the energy cost. It only took 0.644 picojoules of energy per bit to program.
Picojoule, that sounds incredibly small.
It is ridiculously small, ultra-low power consumption. Think about devices running cooler, batteries lasting way, way longer. This is the kind of efficiency leap 2D materials promised.
So it's fast and efficient. What about reliability? You said these things are fragile. Did they wear out quickly?
That was definitely a concern going in, but the results look really strong. They ran endurance tests showing the memory cells could handle over 10,000 erase and program cycles without failing.
Okay, 10,000 cycles is pretty standard for in our flash, right?
It is, so it meets that benchmark. And for data retention, how long it holds the information, they projected a 10-year non-volatile lifetime, even at a slightly elevated temperature of about 55 degrees Celsius. So it looks reliable, too.
Okay, buildable, fast, efficient, reliable. But this wasn't just testing one tiny component, right? You said it was a full chip, a 1 kilobit chip.
Yes, a fully functional 1 KB chip. And they tested it like a real chip, not just isolated cells.
What kind of tests?
They showed it could handle instruction-driven operations, meaning you could tell it what to do using commands, like a real memory chip. And crucially, they demonstrated 32-bit parallelism.
Meaning it could read or write 32 bits of data all at the same time.
Exactly. Which proves the architecture can handle the kind of high-bandwidth operations needed in real computing tasks. It wasn't just working one bit at a time slowly.
And they did one more test, didn't they? Something to really stress the system and make sure neighboring cells weren't interfering with each other.
Ah, yes, the checkerboard pattern test. This is a classic stress test for memory.
What's involved?
You try to program the memory array with alternating zeros and ones, like squares on a checkerboard. This pattern is particularly tough because every cell has neighbors in the opposite state, maximizing the potential for electrical interference or crosstalk.
And if their shielding and modular design worked?
The pattern should read back perfectly, and their accuracy for this test, it was 93.55%.
Still over 93% accuracy on the toughest pattern test.
Yeah, which is excellent. It confirms that their whole system design, the modular separation, the electrical isolation, it actually worked effectively at the chip level to prevent that interference.
So, bottom line, this wasn't just a lab curiosity. They built a fully functioning, high-performance, efficient, reliable, and manufacturable 2D memory chip.
That's the takeaway. The system-level success here demonstrates that this Atom M2CHE approach really does provide that bridge. It takes 2D electronics from, interesting possibility to credible real-world technology. And the power consumption figures they got were comparable or even better than similar commercial silicon nor high flashes available today.
Okay, let's try and wrap this up. Time for our key takeaways from this deep dive into the Fudan University team's 8OM2C Chi-P breakthrough. What's the first big message?
Takeaway 1. We have the bridge. The Atom M2 Chi-P technology provides that missing piece, that systematic industrial blueprint. It successfully merges the super fast but super fragile world of 2D materials like MoS₂ with the tough, reliable world of standard silicon CMOS. It solved the physical and electrical integration nightmare.
Takeaway 2. Warp speed engaged. The performance is real. This 2D NOR flash memory hits that incredible 20 nanosecond programming speed, thanks to quantum tunneling, and sips power at just 0.644 picojoules per bit. This is genuinely pushing memory performance beyond what silicon alone can easily do.
Takeaway 3. Ready for prime time. Well, maybe not tomorrow, but the path is clear. That amazing 94.34% manufacturing yield, combined with the successful full chip tests, 32-bit parallelism, instruction control, passing the checkerboard test, all proves that 2D electronic systems aren't just lab dreams anymore. They are demonstrably viable for the road to commercial manufacturing.
This feels like a really significant milestone. Building this first successful hybrid chip opens the door to a whole new generation of computing, doesn't it? Faster, denser, lower power, impacting everything from our phones to massive data centers.
It really does shift the landscape, but, the researchers themselves hinted at something potentially even bigger down the road.
Oh, what's that?
They pointed out quite rightly that the memory architectures we use today, NOR, NAND, they were all designed around the strengths and weaknesses of silicon. We invented them decades ago to make silicon work best.
Right. We built the system to fit the material we had.
Exactly. So this amazing Atom M2 seed-shaped success story is about cleverly adapting these new, powerful 2D materials to fit into our old silicon-based architectures.
Okay, I see where you're going.
So here's the provocative question to leave everyone with. If this team has proven we can build the hybrid chip, what happens next? What entirely new kind of memory architecture could we design, starting from scratch, specifically built to exploit the truly unique quantum-level atomic properties of these 2D materials?
An architecture designed for the 2D world, not just adapted to it.
Exactly. What kind of performance leap might that unlock? Forget warp drive, maybe that's where we find ludicrous speed.
A future without that spinning beach ball or loading bar. I like the sound of that. Something to think about. Until next time, keep diving deep.